and that won't change the optimizing B, but it'll give us an interpretation of the growth rate of wealth. So I write this as log B of x times O of x, which is 1 over R of x. Then I take this and I say, you know, this looks, summation P log B over R looks a lot like relative entropy. Let's make it look exactly like relative entropy by writing this as log B of x over P of x times P of x over R of x. So the P's cancel, this is an identity. Then we break this into the sum, log B over P plus log P over R, and then take the expected value of the whole thing, because we have this, and this turns out to be minus dPB plus dPR. So that's the growth rate of wealth you can achieve if you believe B. The bookie believes R, the odds maker believes R, and gives you the appropriate odds. And the true distribution is P. So look at the picture. Here's the probability simplex. Here's the true distribution P. Now, the odds are made not knowing what the true distribution is, as if the distribution is R. But you are trying to guess what the true distribution is, and you guess B. Well, this distance is dPB, and this distance is dPR, and as long as you are closer to the true distribution than the bookie, in a relative entropy sense, this will be positive, greater than or equal to 0, if B closer to P, by closer I mean relative entropy, closer to true P than is R. By the way, if you want to feel for dP2 or dPR or whatever, just expand it around R equals P, and you get a quadratic. The first term is sort of quadratic, and it turns out to be the chi-square distance between P and R, and actually half of it, and so on. So it acts like the square of the Euclidean distance locally. Now, if B equals P, then this is the amount by which your money grows. Okay. So that's our first result. What happens, what's the cost of investing in the wrong distribution? In fact, let's just suppose the odds are fair with respect to P. R equals 1 over P. Then your cost is minus dPB, how far you are away. Your money actually will not go to infinity, it'll go to 0 exponentially, but you can be encouraged it'll go as slowly as it possibly can. Remember, you're being forced to bet all of your money on the horses. Okay, now let's look at value of side information. So we have xy drawn according to some probability mass function p of xy. And this is winning horse, which of course is a random variable taking values 1 through m. And this is like track conditions, the amount of weight the jockey is carrying, or whether the trainer has been giving illegal drugs to the horse. So this is side information, and it will obviously affect X. Now the question is how much does it help you to have this side information? All right? So we now have bet B of X given Y equals proportion of wealth bet on horse X when Y equals little y. In other words, what's the true distribution on X? Well, it's P of X. But if you have side information, the true distribution isn't P of X, it's P of X given Y. In fact, that's what, when you go to the racetrack, you already have some side information. That's how the odds are set. That's why you know one horse is even odds to win and another is a 50-to-1 shot. Oh, some quick stuff about horse races. In actual practice, the track takes 17% of the money that's bet and only returns 83% to the bettors. So the odds are unfair. It's as if a mystery horse with probability roughly 1 in 5 is running a race, and if it wins, you lose. That's one way to think of it. All right, so what about schemes for winning at the racetrack? Well, if you always bet on, if you bet in proportion to the tote board odds, B equals P, but you don't like times gamma. If you bet in proportion to the odds, you get only 83% of your money back. You lose 17%. If you bet on the favorite horse each race, those horses are under bet. You only lose 8% of your money on the average. If you bet on a horse at random, you pick a number 1 through M and bet on that, you lose something like 40% of your money. And if you bet on the long shot, you lose even a greater percent of your money. Because long shots that are 50-to-1 should really be 200-to-1. it's human nature to go for those, and so those are overbet. All right. So there's no simple formula for how to win at the racetrack. And if there were, it would be factored into the odds and you would never see it. In other words, the formula would cease to work because it only takes a small amount of smart money to implement the formula and change the odds so that all of a sudden you don't have an advantage. Your formula will just wash out. Okay, back to reality, that is the math of it. We have the following: b of xy greater than or equal to 0, and summation b of x given y over x equals 1 for all y. I think I'll go over here. The expected value now of log s of x is the summation of p of xy, the probability of the horse winning and the side information, log of the amount of money bet on horse x given y times the odds O of x. This is over x and y. This can be written by first factoring out p of y. So it's p of y summation p of x given y log p of x given y O of x. This last term, log O of x, expected value over p of xy, is just summation p of x log O of x, log of the odds. And here we get plus summation p of xy log b of xy summed over x, and then plus sum over y. So we're going to condition on each value of y. Well, excuse me, this is b of x given y. We're going to condition on each y. And now we know immediately that for each y, b should be proportional to p. Here, the conditional p, the conditional b. So this is less than or equal to summation p of x given y log b of x given y. Whoop. And this is now a p. And so we immediately have that our optimal gambling is conditional probability. Makes sense, doesn't it? That's the true distribution, given your knowledge of y. But then this sum, excuse me, there should be a p of x, a p of y here. Can you read that? In other words, summation p of y, and then the sum over x of the conditional. And this then turns out to be minus the entropy of x given y. So this is with side information. And we might call this W star of x